Alright, welcome to this video on a free response question that's dealing with relative mins and maxes, inflection points, and finding an absolute max within a given domain. So this function is the ln of x squared plus 3 minus x, and it gives us a certain domain here. And the first part, A, says find the x-coordinate, only the x-coordinate of each relative max and min on this function. So, of course, the first step would be to take the derivative. So if we do that, we get that f prime of x is equal to, and recall that the ln of x is, the derivative is 1 over x, but we don't just have straight up x here, we have this quantity, squared plus 3. And then it's a chain rule. We have to multiply it by the derivative of the inside stuff, which is 2x. And then don't forget that little piece, minus 1. So we have, clean that up a little bit, we have 4x over x squared plus 3 minus 1. And now we're going to set the first derivative equal to 0. And if we solve that, we would get 4x equals 1. That's all over x squared plus 3. And then we could cross multiply to get x squared plus 3 equals to 4x. Move the 4x over, and we would get x squared minus 4x plus 3 equals 0. And now we can factor this out, hopefully. It's x, looks like a minus 3 and a minus 1. So we know that x equals 1 and x equals 3 are critical points. And I guess we should talk about this fact right here, that the denominator also could give us a critical point, but will that denominator ever equal 0? And the answer is no, because you're squaring a number and adding 3 to it. It'll always be positive. So let's take a look at x equals 1 and x equals 3, and just noting that we're going to stop at 5 and also going to stop at this negative 3 over here, because that's in our domain, right? So start off, we'll look at 0. That seems like a good place as any. And we're plugging it into the derivative. So let me highlight this over here. We can use any derivative that we want, and maybe this isn't the best. Yeah, it should work fine. So what happens when you plug in 0 right here? You get, on top, you get 0. Actually, I should highlight this part right here, right? That's our cleaned up derivative. If we plug in 0, we get 0 on top over 3, which is 0, and 0 minus 1 is certainly going to give us a negative value there. So the graph is decreasing there. And what's happening at 2, let's say? At 2, you plug in, you get positive on top, you get positive 8. And on the bottom you would get 7. So 8 over 7 is bigger than 1, so it's going to be positive here. And I'm pretty sure it's going to shift back to negative, but just to make sure, let's try a 4. You would get 16. 16 on top, and on bottom you would get 16 plus 3 over 19. So we have a number less than 1 right here. Subtracting 1 is going to take it back to negative, right? So that's that. And this will give me enough information to talk about relative mins and relative maxes. Of course, we're not going to use a sign chart to analyze this. Let me erase this part right here. And we know that this is the derivative right here, right? So the justification, of course, this would be a relative min at 1, and the relative max would be at 3, and the justification, of course, written out would be a relative max occurs at x equals 1 because the derivative the sign of the derivative changes from negative to positive at x equals 1 and x equals 1 equals 0 in the derivative. And the opposite of that would be true for the relative max justification. So I'll go ahead and go to part B. Part B says find the point of each inflection. So we know we have to take the second derivative, and of course this is our first derivative right here that we've boxed in yellow. So the second derivative would equal, looks like a quotient rule, f prime times g minus f g prime, which is what? 2x. And then of course the minus 1 over here goes to 0. And then we have to square the bottom. And then minus 0, which is pointless. So now, oh, forgot to square that, didn't I? So we have f prime g minus f g prime over g squared. Okay. Now we're going to do what? Well, let's observe the fact that the inflection point, the denominator, is always going to be positive again. Still the same justification as before. So all we really need to do is consider when does the numerator equal 0. So let's go ahead and we can factor or distribute that to get 4x squared plus 12. And we would get minus 8x squared all over x squared plus 3 squared. And we end up with a negative 4x squared on top plus 12. And on the bottom we have x squared plus 3 squared. And perhaps it'll be a little nicer if we factor the numerator out in our analysis portion here. So I'm going to take out a negative 4, and that would leave me with x squared minus 3 and x squared plus 3. Okay, there's my second derivative with respect to x, and this will have critical points at when x squared minus 3 equals 0, which means x is equal to plus or minus the square root of 3, which is in our domain. So now we're going to take a look at a sign chart for that, and suppose we can do that over here if I just write this a little bit smaller. And we're going to have a negative square root of 3 and a positive square root of 3, and we're going to use our second derivative. And of course, once again, we still have our stop and start points of 5 and negative 3, and looking for concavity, right? Or actually points of inflection. So here it's equal to 0, which is a possible point of inflection if it changes signs. And let's start over here. We could use, say, the number 2, right? Actually, no, we can't. We could use, yeah, we could, because if you think about a negative square root of 4, that is more negative than the square root of 3. So let's use 2. So you plug in a 2, and you get what? Uh-oh. So I can undo that. There we go. You plug in a 2 right here, and you get 4 minus 3, so you get a positive times a negative. So the top ends up being negative, and the bottom, as discussed earlier, is always positive, so that is going to be negative. And then pick a number between that, which a nice candidate would be 0. Plug in 0, you get a 0 squared minus 3, you get a negative times a negative, so the top becomes positive. So it looks like it's, so we have concave down here and concave up here, and we have our first point of inflection. And now we'll go check out the other side. We can just use the number 4 if we'd like. You plug in 4, and you will get 16. 16 minus 3 is positive 13, times the negative is going to end up giving me a negative on top. Bottom's still always going to be positive, so it looks like it does have 2 points of inflection. And so the justification there is the sign of the second derivative of f of x is equal to 0 at when x is negative square root of 3, and the second derivative changes sign from negative to positive there. And likewise, f of x, or excuse me, the second derivative of f is equal to 0 at a positive square root of 3, and the second derivative sign changes from positive to negative there, which is a second point of inflection. Alright, so now that we have all that out of the way, we've already identified our relative mins and maxes, and now part C says find the absolute max value, which means we have to find the y value too. So be very careful when you're encountering these type of problems. So I think I'm done with the second derivative. And let's take a look at part C. And remember, absolute max, you have to check the endpoints as well. But where is our relative max? Our relative max is only at x equals 3. We don't need to check our relative min. And to be honest, if you include this in your analysis, you probably don't even need to check the right endpoint of 5, because this graph is decreasing right here. So if it starts off at a max and it continues to decrease till you get to that end, the only really things you need to check are 3 and negative 3. But let's go ahead and check them all. So here's our relative max. And so what we're trying to look for is what is f of 3. So let's plug it in. We have 2 times the natural log of 3 squared plus 3 minus 3. So that would be 9 plus 3 is 12. So you have 2 times the natural log of 12 minus 3. That's what f of 3 is equal to. Let's go check out the endpoints. Let's check out f at negative 3. It's going to equal 2 times the natural log of 12. Whoops, I didn't even write it down, did I? I assumed that it was going to be that, and I think I might be right this time, because you have a negative 3 squared plus 3 minus a negative 3. Remember my x right here? So if I can slide that down a little bit. Alright, so let's finish this f of negative 3 before this video gets even more boring and more long. We have 2 natural log of positive 9 plus 3 plus 3. Okay. Well, this is kind of convenient, I suppose. Since we have no way of knowing what the natural log of 12 is without a calculator, it makes sense that here at negative 3, we have this quantity, which we also had in the function value at positive 3. Of course, no matter what the number is, whether it's positive or negative, it doesn't matter. If you add 3 to something and you subtract 3 from that same something, this is clearly going to be the absolute max. So, but let's come back to it. Let's see if we can just double check what is the endpoint here at 5. So it's 2 natural log of 5 squared plus 3 minus 5. So this is 2 natural log of 28 minus 5. And I guess that we're sort of stuck a little bit here, right? Because you don't really know what the natural log of 28 is. And you don't know what that is if you subtract 5 from it. So it does turn out that we have to go back and actually use analysis on this, unless you just have those numbers memorized, which I can't imagine anybody would. But let's go back to I started this explanation a little bit. We have our relative max identified, right? And look what happens immediately to the right of our relative max as we start approaching the endpoint of 5 right here. As we approach this endpoint, the function is decreasing, indicated by the first derivative, right? So it is going to be that the relative max either has to be at one of the endpoints or at the relative max, and it can't be at this endpoint because from this relative max the function is decreasing. So that's kind of long-winded. I hope you followed me through this whole thing, and I'll try to put another one up soon.